Continue our program with a really future update on the muon collider, going really to multi-TeV, and Massimo Casarsa will give us an update. I'm looking forward to your invited talk. It's 20 minutes plus 5, and I will give you 5 minutes warning before the end. I'm looking forward to your update.
Good morning to everybody. So I'm going to present an overview of the muon collider project. I will try to highlight the potential and the advantages of a muon collider, but I will also outline the crucial points and the challenges with that such a project will pose on technology and on the experiment. So the main reason why a muon collider is so appealing is the fact that it can provide leptonic collisions in a multi-TeV range. This is due to the fact that muons are heavier than electrons. They don't radiate so much synchrotron radiation, so a muon collider can be built as a circular collider and reach very high energies. Second point, muon is a fundamental particle. So when muons collide, all the center of mass energy participates in the fundamental hard scattering. The figure I report here compares the energy, the colliding energy at a PP collider with the colliding energy at a muon collider to get the same production cross-section for a given process. In this case, we are considering the two-particle neutral current annihilation into a new state. And what can emerges from this comparison is that in general, one needs to pump much more energy at a PP collider to get the same cross-section as in a muon collider. This is due to the fact that hadrons are composite particles, and the constituents collide, not the particles themselves. So both the fact that a muon collider is reaching multi-TeV ranges and the fundamentalness of muons is going to open the way to an unprecedented physics program. First of all, standard model. A muon collider will allow very high precision measurements of known standard model processes, but in an unexplored multi-TeV energy regime. We are expecting abundant samples of standard model particles. The figures on the left represent the production cross-sections for some of the standard model processes and show a very interesting feature of physics at the muon collider. The final states are produced via two main mechanisms. One is the S-channel annihilation, and in this case, the cross-sections are decreasing as 1 over square root of S when the energy increases. The other process is the vector boson fusion, and in this case, cross-sections grow with the energy with the logarithm law. The interesting thing is that at a certain point, from a certain energy on, and this is different from process to process, but from a certain energy on, the vector boson fusion dominates, and effectively muon colliders, high-energy muon colliders, are vector boson colliders. Another important sector of muon collider physics is the X. In this case, the inclusive cross-section is of the order of 1 picobarn, So abundant Higgs samples are expected to be produced. And this will allow precise measurements, for example, of the Higgs couplings to fermions and bosons. But we will also have access to rarer final channels, like the double X and even rarer, the triple X, which can allow the measurement of the trilinear and quartic Higgs couplings, and so eventually defining completely the Higgs potential. Here I just many theoretical papers have come out in the past weeks. Here just I report an example, an estimate of the trilinear self-coupling of Higgs, and the estimate is of the order of a few percent for a, let's say, for an energy of collision of 10 TeV. But the final goal of all the future accelerator projects is to explore the uncharted territory and to investigate physics beyond the standard model. It is the same for the Muon Collider, and there are two ways to explore the unexplored. One, indirect searches. For example, looking for deviations of standard model observables from the predicted values in the standard model. An example could be the triple Higgs production cross-section, which depends on the trilinear and quartic Higgs self-coupling. Deviations from the standard model expected cross-section could be hints of new physics not yet discovered. Another way is the direct search. A Muon Collider has the power of producing new states, new heavy states, up to half the center of mass energy. Last but not the least, the economical aspect. A Muon Collider is the most, at high energies, is the most energy efficient machine. The figure here reports the integrated luminosity per wall power expressed in terawatt hour. And one sees that the E plus E minus circular colliders are at a certain point are beaten by the synchrotron radiation and become less and less convenient as the energy increases. The linear colliders are almost flat. So increasing in energy, the rate of luminosity over power stays flat, while the Muon Collider has a steady rising trend. Muon Collider is not affected by a severe beam Strahlung like in the case of linear colliders. So the beam energy spread is very narrow, of the order of 1 per mil for energies 3 to 14 TeV, and being circular and compact, the footprint is relatively small for a Muon Collider. The other side of the coin is that, unfortunately, muons decay, and such a tremendous physics potential is not coming for free. As we all know, muons decay into an electron, into neutrinos, and both the electron and the neutrinos will make our lives very complicated. The time dilation of spatial relativity comes to help because in the lab we have enough time to prepare, accelerate, and put in collision mu plus and mu minus beam. But during all the life cycle of the beams, muons keep decaying, And so the electrons and then photons radiated by these electrons in the dipole fields interact with the machine elements and produce a constant and pervasive flux of secondary and tertiary particles, which have to be taken into account for both the machine operation and for the experimental apparatuses. All of this has to be taken into account in the design of the experimental complex. A muon collider is also a very intense source of neutrinos, which has some interesting aspects. For example, this can create very interesting and constructive synergies with the neutrino physics, but this may also represent a problem, since neutrinos beams are very intense and at very high energy. So when they emerge, even many kilometers away from the accelerator complex, when they emerge from the Earth's surface, they can activate the materials and represent a radiation hazard for the population and the environment. So this it's imperative to mitigate the radiation field at the surface. There is a team at CERN studying the orography of the area to assess the impact of a possible muon collider in the LHeC tunnel. The goal is to keep this radiation well below the legal limit, which is 0.1 millisievert per year. According to some extensive studies conducted by the muon accelerator program in US, we are safe at 3 TeV, while at 10 or greater energies, we need to have some mitigation in place. This cartoon schematizes the main elements of a muon collider facility. The muon injector, which consists of a source. Here muons are produced as tertiary particles. A beam of protons hits on a target, producing pions. Pions are let decaying, and then the muons are collected. A crucial point here is the cooling. The produced muons have very different momenta, pointing in different directions, and they have to be cooled and collimated in order to be packed into bunches and then in an effective beam. When we speak of muons, time is very important, and so they have to be accelerated as quick as possible, because the faster they go, the slower they decay. So there is a pre-accelerator stage, which brings muons to energies of some 100 GeVs. And then muons are injected into an accelerator ring, where they are brought to the nominal collision energy, and then injected into a collider, where up to now 2 interaction points are considered. So the background caused by muon decays represents the major source of machine background in a muon collider. The amount and the characteristics of such a background depend on the energy and hence on the machine optics, the lattice elements, and on the machine detector interface. To study this background, a Fluka simulation has been set up, which integrates the full machine design. for a muon collider operating at 1.5 TeV. The machine design was developed by the muon accelerator program. The picture here shows a zoom of the FLUCA model. The FLUCA model comprises half the accelerator ring, and this is just a zoom around the interaction point with the collision hole and the detector. And it shows a mu minus beam entering from the right. You see all the electromagnetic showers produced by electrons and photons hitting the machine elements. Electrons are captured by the beam and are transported along the muon beam. Two important elements which were devised by MAP are two tungsten cones which are inserted into the detector and work as shields. These are reducing the background entering the detector by a factor of, on average, 500. And here is where we consider the neutrons. There are a lot of neutrons going around all over the machine tunnel and the detector.
You have 5 more minutes.
Okay, I will be quicker. So, interesting feature of this background is that particles entering the detector may be produced by muons decayed tens of meters upstream the interaction point, as is shown in this picture. So, main component are photons and neutrons. Then we have electrons and minor amounts of charged hadrons and muons. As for the kinematic characteristics of this background, it tends to be very soft. The electromagnetic components have average momenta of a few MeV. The hadronic component, which is mainly neutrons and protons, around half a GeV. The more energetic component is represented by the muons, and we estimate the average momentum to be in the range of 10 GeV. The statistics is very low to have a more precise estimate. Another feature of the particles from the beam-induced background is the timing. They tend to be asynchronous with respect to the bunch crossing. There is some component synchronous, which is given mainly by electrons and photons, which escape from the beam pipe, which is not shielded, of course. So a vast campaign of simulation studies is underway with full simulation. The first ones are focusing on the detector response to the mainly to the BIB, because the game will be to cope and deal with this beam-induced background. We are using a detector based on the click model, but the machine detector interface developed by MAP has been inserted inside the detector, which means the two tungsten cones and the vertex detector. So as for the tracking, the tracker is the detector closer to the beam line, so is the most affected by the beam-induced background. And the graph here is reporting the heat densities in different tracker layers. The first two peaks, the very huge peaks, represent the density on the first layer, which has two sublayers. So the strategy for tracking is to reduce as much as possible the heats before starting the tracking. Otherwise, the combinatorics will kill the tracking procedure. And the main handles we are using to do this are high precision timing. And here is an example. Reading out only the heats in some narrow time window compatible with the punch crossing, we reduce by a factor of 3 the background. Then very effective is the double layer pointing. Using double layer, we can point towards the interaction region, and then the pixel cluster shapes. Plots on the bottom are showing an example of performance in the case of particle guns with the beam-induced background overlaid. What we see is that in the central region, everything is fine, and problems start to arise when we move to lower angle and towards the beam line. For the PTs, again, for PT greater than 1, the effect is very mild, while it becomes significant at low PT. For the calorimeters...
Now at the end of the nominal talk time.
I have 2 slides, okay.
Thank you.
So, for calorimeter, the BIB is depositing almost uniformly the energy on the ECAL and the HCAL. In the ECAL, mostly we have photons and neutrons, while for the HCAL, practically only 99% of neutrons. Also for calorimeters, high granularity, fine longitudinal segmentation, and precision timing will be the main players in coping with the background. Muons are relatively safe. In the barrel, the effect of BIB are negligible, while may have some effect on the end caps in the region. This is a projection of the hits on the muon detectors end caps, and you see in the region close to the beam line, we have some noise to be taken into account. Performance on the bottom are shown for muons particle gun without the beam-induced background, but in the case of the central region, it makes no big difference. Another set of full simulation studies focuses on physics. This is just the first example of a channel, estimation of the yield in the channel HH, with H is decaying into B quarks at 3 TeV, and the signal is extracted fitting the output distribution of a boosted decision tree, and in 1.3 attobarn of data, we estimate an yield of 70 signal events with an uncertainty of 22–23%. There will be an update of this study for the next APS conference. So the Muon Collider project is going to present unprecedented technological and experimental challenges along its way, but the final reward will be an extraordinary and unique physical potential. The Muon Collider project is getting a lot of momentum in the past year. An international Muon Collider collaboration is being formed, which has the main objective of assessing the potential of a Muon Collider and identifying an R&D and the costs of a path to demonstrate the feasibility of such a collider by the next European strategy of particle physics. There is a forum is being established on the Muon Collider, also in the ongoing SNOMAS process. And I think I'm concluded with this. Thanks for your attention.
Thank you very much, Massimo, for this very interesting talk about the challenges for Muon Collider, but also the physics capabilities which come with it. This was really very detailed and very interesting. Are there questions to the talk? Well, let me then just ask one. Let's assume the most optimistic scenario of what could be a possible timescale for an international Muon Collider.
Yeah, so the first step will be the next European strategy update in 5 years. At that point, we would like to be ready to start the R&D for a CDR. So and then would require like I think 5 or 6 years, and at the end of the CDR we will be ready for approval. So I think 10, let's say 15. Let's be safe. 15 years to be ready to ask for approval. And then the construction will take 5, 6. I don't remember how many years.
Okay, thank you. Thank you very much. Even so, I now see another question raised. We unfortunately have to go to the next presentation.
I will answer on the chat.
Yeah, please put the question in the chat. That's great. And thank you very much again. So we now switch to an existing experiment, E plus E minus Belle 2, where Kavita Lalwani will give us an update on the status of Belle 2 and future plans. We are looking forward to your presentation. I also will give you a 5 minutes warning.
Okay, so should I share?
Please, yes.
Okay, just wait. I can share the screen. Can you see the screen?
Yes, not yet full screen, but okay. We see your screen.
Is this now in the full screen?
Now it's in the full screen, yes. Perfect. Thank you.
Okay, so should I start now?
Yes.
Yes, but just hold on. I have to keep this view away, otherwise my presentation is... Okay, so just hold on. Able to minimize it. Okay, so myself, Kavita Lalwani, faculty from the Department of Physics, MNIT Jaipur, India. On behalf of Belle 2 collaboration, I will today talk on the Belle 2 experiment, where I will present the current status of the experiment and the prospects in terms of the detector performance as well as in terms of the physics results. So I'm on the slide number 2. Here is the outline. In terms of introduction, I would briefly give you an overview on the Super KKB and the Belle 2 detector. Then I will come on and to discuss the performance of the Belle 2 detector and the subsystem. And then I will highlight the important results on the physics or the various aspects of the physics at Belle 2. We are working, and I will summarize and conclude my talk. So I'm on the slide number 3 here. Here is the Super KKB. So you can see the Super KKB is an asymmetric E plus E minus collider, which is located at Keike, Japan, and where we have the electron energy of 7 GeV and the positron energy of 4 GeV, and the center of mass energy is 10.58 GeV. Here you can see the long tunnel of 3 km of the Super KKB. The important feature I want to highlight is it uses the nano beam scheme in order to achieve the higher luminosity. So the design higher luminosity is 6 × 10⁵ per centimeter square per second. So in order to achieve this high luminosity, the basic idea is to reduce the vertical beta function at IP and increase the beam current. Hence, we can achieve this high luminosity. So moving to the slide number 4, here is the Belle 2 detector. So just hold on. Okay. So Belle 2 is the multi-purpose detector system, and it is located and installed at the interaction point of Super KKB. And here we have a various sub-detector system at Belle 2 for the different measurements, such as near the origin, we have a pixel detector, silicon vertex detector, and the central diff chamber used to measure the decay vertex position and the tracking of the charged particle. Then we have the top and air edge used for the particle identification in the barrel and the end cap region. And we have then electromagnetic calorimeter, which uses cesium iodide crystal with thallium doped to measure the energy and of the photon and electron. We have a KLM detector, which is used to identify the kaon and muon. Our aim is to achieve the integrated luminosity of 50 autobahn inverse by 2030. And as today, as of now, we have collected the data at 119.26 femtobarn inverse. So moving to the next slide, the performance of the Belle detector is carried out by on the basis of the working of their subsystem. So on the left hand side, you can see the particle identification plots for kaon and muon separation using the d star going to d pi and then d going to further k pi. Here on the y-axis, I have shown the particle ID efficiency and the miss ID rate as a function of the lab momentum tracks. And you can see we have moreover greater than or equal to the 80% efficiency of the kaon ID, and we have also compared our results for with the Monte Carlo, and they are in agreement. Now moving to the right hand side, where I have shown the performance of the Belle detector through the tracking efficiency using the E plus E minus going to tau plus tau minus decay, where one tau decays into the leptonically and the other tau decays into the hadronically into the charged ion. So on the y-axis, I have shown the efficiency times the detector acceptance as a function of the track PT, and you can see our results are in agreement between the data and Monte Carlo. Now moving to the next slide, the performance of the Belle detector is also shown with the good reconstruction of the neutral particle such as pi 0 and eta. Here the plot is shown for the pi 0 reconstruction from 2 photon events. Now moving to the downside, bottom side, we have also checked the performance of the Belle subdetector system by measuring the flavor tagging, which is of the important physics such as CP violation and BB bar mixing. In the flavor tagging, we report here the first calibration results of the standard Belle tagging with 2019 data at the integrated luminosity of 8.7 femtobarn inverse. So what we have measured the efficiency of the tagging efficiency and the fraction of the wrongly tagged events. And we have also measured this for neutral B candidates, the efficiency, total effective efficiency is 33.8%, and our results is also compared with the Monte Carlo, and they are in agreement, which explain us the understanding of the performance of the detector system. And we also compared our results with the best from the obtained from the Belle, and we are in agreement. So flavor tagging will be the fruitful input for future calibration for the measurement of the CP symmetries. Now moving to the next slide, we have a huge physics list at the Belle through I have shown through the flowchart. So for example, charm physics, CK metric elements, where we measure the phi 1, phi 2, phi 3 CK angles, time dependent measurements, rare B decays. Now on the left hand side, we have a dark sector, tau physics, and many more. I hope you had visited the results, important results on the charmony and photonium presented by our collaborator Ashish Thampi in the yesterday talk. And in the further slides, I would like to highlight the important results on various aspects of the physics we have been achieving at Belle 2 step by step. So here, moving to the slide number 8, as we have seen, we have a good flavor tagging efficiency at Belle 2. So it is our good opportunity for all of us to measure the CP violation by measuring the CKM angles such as phi 1, phi 2, phi 3, using the various B decay modes as shown by the two important variables such as delta E and MBC. What is MBC? It's a beam constrained mass and defined through this equation. So I will start with the top, where we have B going to GEPSI KL, and GEPSI is reconstructed from E plus E minus. Here the delta E distribution is shown, and these are the new results for 2021. We have clear signal along with the combinatorial background. So this is the important measurement for phi 1. And now moving to the downside, bottom side, we have a B going to gypsy K short. These results we have obtained in the last summer for the which can be used to measure the phi 1. Now moving to the left hand side, where I have shown the top plot B going to 2 neutral pion. This is a unique decay because we have a 4th proton in the final state Belle 2. These are the new results, and analyze at the data collected 62.8 femtobarn inverse. This is the unique measurement for phi 2 measurement, and on the downside, bottom side, I have shown the results for B2D H, where H is kaon and pion, and the delta E distribution is shown, where we can see the kaon enhanced data along with the BB bar and QQ bar background. So now moving to the slide number 9, I would like to highlight the important results on the charm physics. First, I would like to highlight the decays, results from the decays, which is used to measure the time integrated CPS symmetry. So on the left side, top side, I have shown the delta M distribution for D0 decay into K short, and delta M distribution for D0 into K short pi naught. What is delta M? The delta M is the difference between the mass of D star and the mass of D0. So we have clear signal, and you can see the left hand side is the new results for 2021, and we can see that the resolution and the background level is comparable with the Belle, while we analyze the only data of 1.5 years of the data taking. Now moving to the bottom side, we have shown the important results on the D0 lifetime measurements. The left plot shows the D0 lifetime measurements for 3 different decays, such as K pi, D0 decay into K pi pi, and K3 pi. Our results are in agreement with the world average value, and here the error bar on the data is statistical only. Now moving to the right hand side plot, in the bottom, we have shown the time resolution at Belle 2 and compared with Belle and Babar. You can see our time resolution is 2 times better than Belle and Babar. We thank for this to our improved vertex detector and the nano beam scheme used in Belle 2 at Super KEKB. Now moving to the next slide, which is slide number 10, I'm showing you the important results on the D0 bar mixing. Here you can see on the top, I have measured the ratio, which is the ratio of the signal yield of wrong side events to the right side, to the wrong side to the right side, D0 decay into 3 decay modes, where D decay into K pi, D decay into K3 pi, K pi and D decay into K3 pi. So our results are in agreement between the world average, and we have analyzed the data at 37.8 femtobarn inverse integrated luminosity. Now moving to the downside, I have shown the results for the decays, which is used to measure the time dependent knowledge analysis. On the left side, you can see the Q release energy plotted for the decay D going to K short plus pi minus. These are the results which you can see, where the resolution of the release energy is better than 2 times, is a factor 2 better than the Belle. Now moving to the right hand side, bottom panel, you can see the delta M distribution is shown at integrated luminosity 72 femtobarn inverse for D decay into pi 0 pi plus pi minus. These are our new results, where we measure the signal yield per unit luminosity. Now moving to the slide number 11, here I have shown the charmless B decay results. So as we all know, the isospin sum rule is proposed for measuring the isospin for the B decay into K pi system. Here through this equation, big equation, here this measurement, we have the limiting factor input by the AK pi, where AK pi naught is the CPS symmetry for the K naught pi naught system. Here I would like to highlight, we have 2 challenges over here. First is the pi naught as a final state, where delta E fails, and the second is the CP eigenstate. For that we need a flavor tagging. So here the yield is measured for B going to K naught pi naught system. For upper plot is the both plots are for MBC distribution for B naught and B naught bar. Both are new results for 2021. And now moving to the right hand side panel, here I would like to highlight that we have shown the sensitivity of the isospin for B to K pi system as a function of the time progresses. Here the dashed line represent the projected uncertainty without the Belle 2, and with red one shows the projected uncertainty with Belle 2. So we can see with the Belle 2, the uncertainty on the I measurement is improving. Now moving to the next slide, which is slide number 12, I'm showing you the results of B2K-nu decays. As we all know that the B2K-nu transition is mediated by the virtual G boson as shown in the left-hand side, and the standard model prediction for the branching fraction measurements of the B2K-nu is quoted 4.6 times 10 to the power minus 6 with the quoted uncertainty. On the left-hand side, the data and post-fit prediction for the signal region and the control region bins is shown as a function of PT for this K-nu. And now moving to the right hand side, we have measured the branching fraction as a function, branching fraction at the data at integrated luminosity of 63 femto1 inverse. Our data is agreement with the world average, and we also compared our data with the existing or the other measurements which have been taken with the largest statistics, and our results are very close to those which have been taken with the higher statistics. So this is very good news for us. Now we are moving to the slide number 13, where I have shown the tau mass measurements. This is results. So we know the tau mass measurements is measured at the Belle 2, that the pseudo mass method in the blinded analysis procedure through this formula. So you can see here E beam is the energy of one of the beam energy in the center of mass, and E3 pi, M3 pi, E3 pi, and the P3 pi is the mass, invariant mass, energy, and the momentum of the 3-pi system. And here we have measured the mass of the tau lepton at 8.8 femto1 inverse of about 1,777 MeV per c square, and we compare our results with the world average current value, and they are in agreement. We also compared with other measurements of the tau lepton mass, and we can say that our results on the Belle 2 for this tau mass measurement will be dominated statistically until we obtain 50 autobahn inverse of the data. Now moving to the slide number 14.
You have five minutes left.
Yeah, I'll wind up. I have only 2 slides. Okay?
Perfect.
Yes. So here I would like to highlight the results on the related to the dark sector at Belle 2. This is our paper. You can go through for the detail, and I would like to show you a glimpse on these results. So here we first search for this invisible decay of jet prime through following 2 processes. So upper panel I have shown the L mu L tau model, where E plus E minus going to 2 mu plus mu minus jet prime, and lepton flavor violation scenario is shown on the lower panel, which is the bottom panel, where E plus E minus going to E mu z prime. And here we reconstructed the recoil mass spectrum of mu, where you can see we there is no anomalies observed below the 3 sigma local significance. And we put the 90% confidence upper limit on the coupling constant. To coming back to the LFP scenario, we also measured the reconstructed recoil mass of the mu, and we observe also here the no anomalies for the 3 sigma local significance within below the 3 sigma local significance, and we put here 90% confidence level upper limit on the signal times signal efficiency times the cross section. Now moving to the slide number 15, I have shown I would like to highlight the important results on the dark sector from the axion like particle. So here you can see we have either 2 photon final state or 3 photon, where E plus E minus going to gamma star and then A going to 2 photon. So here the signal is identified by a peak in the recoil mass invariant mass spectrum and the 2 photon invariant mass spectrum. So here we have shown the expected upper limit and the observed upper limit on with the 95% confidence level as a function of MA. We observe no evidence on the excess events for the ALPs, and then we apply the 95% confidence level on the photon coupling here. And we have shown this region at extended occlusion region at 0.5 of femto1 inverse. The results are detailed, you can find in this paper. Here is the list, the publication list, just an overview. We have a 2 PRL paper and the Q conference paper from the recently obtained from the Belle 2. Here is the summary, so I will not read those summary, but I would mainly highlight that the Belle 2 is working fine since phase 3, since 2019. For now, we have achieved 119.26 femtobarn inverse. We have to reach to 50 autobarn inverse, and we are hope that Belle 2 in coming years will give us new physics and will improve the measurements of the standard model. So stay tuned for more results, and I would like now to thank you all for your kind attention.
Thank you very much for this presentation and really a thorough overview about all the physics at Belle 2. Questions for Kavita? I not see any hands up. So you mentioned phase 3. Are there long-term plans beyond phase 3?
Yes, so we will run Belle 2 till 2022, and we are projecting that we will get summer 2022, and we will get there approximately 700 to 800 femtobarn inverse, and then we will make a long shutdown and where we will replace upgrade the pixel and the silicon vertex detector as well as top PMTs, and there will be a long shutdown at 2022. Yes.
Okay, and then after that shutdown, do you have prospects how long you plan to run?
Yes, so approximately I don't remember the year, but yes, we have, I think, a very long shutdown of 1 to 2 years. I'm not sure quite, but we will have that long shutdown. Yes.
Okay. Any other questions or comments on Belle 2, all of their measurement and their future plans? If not, then let me thank you again. This was very interesting. Now we have 3 contributed talks, and the first one is about an upcoming experiment at LHeC, the LHeC, and we will hear about the determination of Parton densities in the proton. Claire Gwenlan will present.
Hi, so it looks like I can share. I'll just try and do that. Full screen. So is that okay? Can you see the full screen?
Yes, it's full screen, and I will give you a 5-minute warning before the end. Thank you.
Okay, great, thank you. Yes, I'm going to talk about the prospects for PDF determination at a future proposed collider, the Large Hadron Electron Collider. So I'm going to be focusing on the results from a recent update to the conceptual design report, and you can find that at this archive reference. Oh, sorry, bit of trouble changing slides. That's annoying. Oh, there we are. Okay, I think it's just a bit slow. Okay, so just to set the context, I'm showing plots to kind of illustrate the situation as it exists today in terms of PDFs and their uncertainties. So this on the left is showing the gluon uncertainty for a number of modern PDFs, and then on the right I'm showing some example PDF luminosities where you can essentially just read off the uncertainty as a function of the invariant mass of the final state that you're interested in. So I think we all know, but what you notice immediately is that in the very large X region, the uncertainties are large. So this is a region relevant for BSM searches, for instance, at the LHC. And then in the very small X region as well, uncertainties are very large. And that's where we expect the onset of new QCD dynamics. And then even in this medium X region where we know the PDF's best, that's the region that's relevant for precision standard model measurements, such as the mass of the W and Higgs production. And certainly we want to measure things very precisely in this region, since small deviations can indicate BSM physics. So we need to really improve our knowledge of PDFs right across the board, and indeed PDFs together with alpha S are becoming the limiting factor on many measurements of interest. Something else to point out as well is that modern global fits, of course, use a wide variety of world data and are increasingly using LHC data itself to constrain the PDFs. But in principle, they're new physics already in the data, certainly in the high mass tails, for instance. And so it's going to be very important as well to make sure that you don't inadvertently absorb BSM effects into the PDFs. And that's not necessarily a trivial issue when you're talking about LHC data as described in this recent study here. So I'm going to be talking about for very high precision PDF determination from external to the LHC. So using this LHeC machine, which is a proposed high energy EP collider. So it's basically a big HERA machine. So I think we all know that DIS is the cleanest and most precise microscope for the study of matter. So this would require the construction of a new electron accelerator. So it would be energy recovery LHeC technology attached either to the high luminosity LHC, so that's what the LHeC is, or it could in a future incarnation be attached to the future circular collider, and that's what's called the FCCEH. So the electron beam energy would be up to 50 or 60 GeV, and for the LHeC that means a center of mass energy about 4 times bigger than HERA. The FCCEH even bigger, and the integrated luminosity would be about 1,000 times that of HERA. So if you want to find out more about the actual LHeC machine and also the status of an ERL facility that's being developed at Orsay as a demonstrator for the LHeC, then I can direct you to these 2 talks elsewhere in this conference. One of them is just in the next session, I think, in this session, but after the break. Okay, so the CDR update was submitted to the archive last summer. It's just been accepted by JFISG, so it will come out very soon. And it's a compilation of new and updated studies since the original CDR in 2012. And I'm going to concentrate in this talk on the results on precision QCD and proton structure. And how also that then can transform the LHC into a very high precision facility. It also has an extensive physics program in its own right, though, and you can see that from the list of talks that are elsewhere in this conference that I can direct you to if you want to know more about the other physics parts of the physics program. Okay, so here's the X and Q squared plane. So the yellow is the coverage of HERA, so that's the world's first and still today only EP collider. The LHeC coverage is then shown in blue here and the FCCEH in brown. So we're talking about an extension of factors of 15 or 120 respectively in both Q squared and 1 over X reach compared to HERA. So that's really an unprecedented increase in kinematic reach for DIS. So this enables precision PDF determination up to close to X of 1 and also exploration of this very small X region here. And crucially, it's very theoretically clean. So although the LHeC has an EA program, this would be EP collisions. And so you've got no nuclear corrections. You access high X at high Q squared, so no higher twist. And also at that time, n cubed LO theory will be about, and so we're talking about n cubed LO PDFs as well. And also experimentally, it's very precise as well. We've got the precedent set from HERA, the HERA combination and the HERA PDFs, in contrast perhaps to the global fits that use a wide variety of world data, sometimes suffering from tensions between data sets and the complications that gives, and also sometimes difficult to understand correlations within and between data sets and this kind of thing. Okay, so the goal of the LHeC PDF program is to completely resolve all Proton PDFs and determine alpha S to per mil precision. So this here shows the coverage of the simulated pseudodata that we used for the study. So it's the inclusive, neutral and charge current data, plus some semi-inclusive heavy quark data as well. And in terms of timeline, the LHeC could, the earliest it could be installed would be in long shutdown 4 of the LHC. So that's kind of early-ish 2030s or so. And that would give several years concurrent operation with the high Lumi LHC. And then you'd want a dedicated run as well afterwards to get the whole data set required for other aspects of the physics. So in the next few slides, I'm going to show PDF projections for 2 different scenarios. One of them, which I'll be showing in yellow, will be for the first 3 years of LHeC operation. So that would be a PDF set that could be delivered quickly to the LHeC experiments so that they could use it in their analyses while the LHeC is still in operation. And then for comparison, I'm also showing a projection from the full inclusive data set. So that would be about an inverse Ataban of electron data. There's a few other details here as well, notably a little bit of positron data in there as well. All the details obviously in the CDR write-up. So the methodology for the fit closely follows the HERA PDF, but also that's detailed in the write-up. Okay, so the first results I'm going to show are the valence quarks here, the U and D, and the blue and yellow are the LHeC projections that I've just spoken of compared to various global fits. And you see there's very high precision determination across the full range of X. So that's going to be of importance for BSM searches at high X, also for precision standard model measurements, as well as being able to resolve the long-standing mystery of the D over U ratio at high X, which we've heard speak of several times in the conference, including the plenary on Monday. And notably, the majority of the improvement comes already from the first 3 years of running. So that's what's shown in yellow. You do see an improvement, particularly in the D, from using the whole data set. That improvement largely comes from the addition of just a small amount of positron data that gives additional sensitivity to the D quark. Okay, so here's the gluon, and here on the log X scale, I'm sort of zooming in on the low X region. So the LHeC data would extend the HERA coverage by a factor of about 15. So down to X values about 10 to the minus 6, FCCEH even further down by another order of magnitude or so. So this would allow the real, precise exploration of small X QCD, and I'll talk about that a bit more in a minute or two. And then on this linear X scale here, we're kind of zooming in on the high X region, where the gluon is small and currently very poorly known. And here is the LHeC projection. So this is quite high precision, and will be very crucial for BSM searches. So as well as the inclusive data that that has been included in these studies, the LHeC will have very high efficiency for heavy quark tagging as well, so enabling to pin down the strange, charm and beauty as well. So for instance, the LHeC will have direct sensitivity to the rather poorly known strange via charm tagging in the charge current process, and this will allow an XQ² mapping of the strange density for the first time. And in addition, measurements of F2 charm and F2 beauty, which were performed at HERA, will have an enormously extended range and much improved precision compared to the measurements that we've had before. So this allows you to basically decompose flavor of the quarks and get a handle on all the PDF flavors, gluon, and all the quark flavors. So here's the summary. This is representing the situation today compared to what we might expect after the first 3 years of running, with further improvements expected after the full running period, and if you include heavy quark data and perhaps other data sets like DIS jets, which aren't yet included in this study. Flash up the
5 more minutes.
Okay, flash up the PDF luminosities as well. So yeah, just showing how precise these are expected to be across the full range of invariant mass. Okay, so this I'm going to flash up only very quickly because this will be talked about in more detail by Ludovica in a talk tomorrow. But this is demonstrating the impact on the LHC. Maybe I'll just highlight a couple of points here. So as we've seen, these will be very precise PDFs, reliable, clean experimentally and theoretically, but also external to the LHC. So this will enable impact for new physics searches. Here, for example, it's an example of a SUSY cross-section. If we could get the uncertainties down from these big bands down to the LHeC projection, that would translate into extra mass reach of 0.5 TeV or so. Here's an MW projection where PDF uncertainties are currently dominating, and the LHeC would allow the PDF uncertainties to be subdominant to the statistical for the first time. And then here, Higgs, for example, I'm sure this will be talked about in more detail tomorrow, but this is Higgs predictions with each of these boxes representing the PDF uncertainties on modern PDF fits. And if you look at boxes of the same color, this shows the sensitivity of the prediction to the alpha S value compared to what you'd expect expect from the LHeC. This is both PDFs and alpha-S uncertainties. Alpha-S I'll talk about at the very end of the talk. And so you're essentially almost eliminating these uncertainties, which will have a huge impact on Higgs properties such as the couplings and so on. So I'm going to have to skip over this very quickly, but I can again direct you to a dedicated talk on the small x region by Anna. That's tomorrow. But I just still wanted to say a couple of words because it's a really unique part of the LHeC physics program is this exploration and reach down to small x. So we expect the breakdown of DGLAP at small x and the onset of things like BFKL and possibly nonlinear evolution and ultimately Parton saturation. And we believe we've seen evidence for the onset of BFKL even in the HERA data at low q squared and low x, where you see if you include some small x resummation effects, you can suddenly describe this turnover in the cross section, which you couldn't before. So this small x resummation is intimately connected to BFKL effects. And the LHeC and FCCEH will have reached down to much smaller x, and so will really give unique power to explore this region. The impact on the gluon is quite sizable. So this shows in the yellow what the gluon looks like if you include small x resummation compared to if you don't. And that has an impact on LHC and future PP collider phenomenology. For example, this is the GGH production cross section shown as a ratio. That's without, and this is with the small x resummation effect. And you can see that as we go higher in collider energy, these effects are quite sizable. So it's going to be really important to understand the correct treatment. And that's what the LHeC and of course FCCEH in the further future can do for you. These are, for example, predictions of structure functions in the red without and the blue with small x resummation compared to the pseudo data, this very precise pseudo data from the LHeC or FCCEH with uncertainties much, much smaller than the difference between the predictions, and FL even more sizable differences. So this means that these data will really have very large sensitivity and power to discriminate between the different small x treatments. Just flash this up quickly. This is a potential prospect for an FL measurement at the LHeC. In red, it would require periods of dedicated low energy beam running, but this is compared to what we did actually do at HERA. So this will be a very powerful extra handle. This I'm going to have to skip over, but I knew that already. So Anna reliably informs me she's going to cover this, but what this was, it would take too long to explain here, unfortunately, but what this was is a study of the power of the LHeC to identify or saturation effects in the data, basically. And I'll give you the tagline. You can ask me about it later if you want, that the LHeC indeed should be very powerful to identify saturation. Okay, so the last thing I want to talk about is the strong coupling. So this is the least well-known coupling constant. The world average currently has about a 1% precision, and the PDFs plus alpha-S together are the dominating theory uncertainty on Higgs production predictions, for example, just as one example. So it's very important to pin it down together with the PDFs. Also other open questions. This is a summary of the alpha-S values from the PDG, and you can see there's quite a range in the central values. So there are open questions as to what is the true central value, what's the true uncertainty, and also historically alpha-S extracted from DIS has been lower than those that extracted in JET data, for instance. So that's also a question that needs resolving. So here are some projections for the alpha-S prospects from the LHeC. One way of extracting it would be to use JET data. So you can fit JET data to state-of-the-art theory. So next to leading order QCD is state-of-the-art right now. Here's a value that was extracted using LHeC pseudodata, JET pseudodata. This corresponds to just a little bit better than 2 per mil. You can also fit to subsets of the JET data. So all these black points correspond to separate alpha-S extractions as a function of scale, and test this running over 2 orders of magnitude. And notably, the uncertainties on every single one of these black points up to a scale of 200 GeV is actually better precision than the current world average. So this will be hugely powerful. Another way to extract alpha S is in a simultaneous PDF plus alpha S fit. So that's also been done with pseudo data. If you were to just use inclusive data, you get about a 2 per mil precision again. And if you want to go for ultimate precision, you could include inclusive DIS as well as jet data. So these are the results summarized by these upper 3 points. The lowest one here is what you would get just using inclusive data, but from the first 3 years. So already, you're getting better than the current world average. As soon as you start to include jet data as well, you get very high precision, even early on in running. So we're talking about an achievable precision on the per mil level. So that's about the same as the FCC EE and sufficient to challenge QCD lattice calculations as well. So just to summarize, the LHeC is a proposed future energy frontier EP collider, and would really, a machine like this would really just transform the physics capabilities of the LHeC. So it would enable precision PDF input external to the LHeC, completely unfolding all the quark flavors and gluon. The results I've presented are documented here, but soon to appear in JPhysG as well. And you can hear more about the rest of the physics program in a number of other talks in this conference. And if I wanted you to sort of take away 3 main points, it would be these in red, which just highlights the fact that we've seen that all the critical PDF information can actually be obtained early. You don't need the full LHeC data set to do it, which means it can be used in parallel with high-Lumi LHC operation. Alpha S is possible to about the per mil level, and also that's achievable early if you use DIS jet data. And these machines, or this machine, or the FCCEH that would come in the further future, really have access to a very novel kinematic regime in the small x region, allowing us to explore small x phenomena such as saturation. Okay, thank you.
Thank you very much for this really great talk and about precision physics you can do with LHeC. Are there questions for Claire? There's one question. Please go ahead, Daniel. Daniel, in case you're muted, we cannot hear you.
Now can you hear me?
Yeah, now we can hear you.
Claire, beautiful talk. I think there are no doubts that the LHeC will be a superior PDF experiment. But one question you made up at the beginning, the point with the impact from LHeC on the PDFs. So basically the complementary, or basically how much LHeC contributes. You're much closer to the experiments nowadays. The basically are the PDFs or the data from LHeC that will reduce the PDF uncertainties statistically limited or systematically limited? Because I mean, I imagine if they are systematically limited, then basically the experiment cannot make use of this PDF any longer.
Right. So hopefully I'm going to answer what you actually asked. Correct me if I misunderstood what you're saying. So right now, the data sets that are being included, some of them are already systematically limited, as I'm sure you know. So for example, the inclusive WZ data that is quite powerful to constrain quarks is being used by the global fitters. That is basically the highest precision we're ever likely to get on that, right? We've already done probably our best job. There is still room for improvement in, for example, top data, jet data. As we get more data, will improve the statistics, especially going into the higher PT region and things like this. Also, there have been studies on what we can achieve with the high luminosity LHC, and there are some improvements we can do with that, because the measurements that the simulated measurements that we used were specifically designed to look at measurements that are currently statistically limited, and therefore you'd get some improvement. So there will be some improvement from the high Lumi LHC, but as you say that it's not, well, you saw the very small uncertainty bands that I presented, but I tried to highlight that there was more to it than that in some sense, right? Because DIS is so clean, both experimentally, but also theoretically. And that is what you don't have with the LHC. We're having trouble even now fitting the data sets that we have, because it's very difficult to understand the correlations, for instance, in a way that it probably won't be for the LHEC. Plus, the thing that I mentioned kind of off the cuff at the start, that the LHC data, particularly in the tails, which is where there is still room for improvement in statistics, could be contaminated with new physics itself. So there's just this huge wealth of benefit that comes from this external, clean, process that is DIS, essentially.
Thank you very much. So
great, thanks. Yeah.
We need to go to the next contribution. I see that there's one more question, but unfortunately we're ready for this contribution 3 minutes extra. So we come to another topic which was prominent at HERA, and that is heavy flavor physics and jet studies. And Xuan Li will give us an overview what we will learn about that at the upcoming Electron-Ion Collider in the US. Thank you.
Thank you, Max, for the nice introduction. I would really appreciate the nice opportunity provided by the organizer to let me talk about the hyper and jet study for the future Electron-Ion Collider. Let me see. Okay. So in my presentation, I will just discuss about why and how to measure high-flow products as future Electron-Ion Collider before as EIC. And also I will introduce ongoing detector design and development to realize the EIC high-flow environment. Following by that, I'll also show you some like a nice reconstruction and also basic projections of open high-flow hydrogen and jet studies of our simulation. Finally, I'll give you a summary and outlook. So I want to give you a brief introduction about the Electron-Ion Collider. It's actually we're using the high luminosity, high energy electron proton and electron nucleus collisions using the existing relatively heavy ion collider hydrogen rings with certain upgrade to study several fundamental questions in the high energy nuclear physics field. So the future EIC has already achieved the CD0 statement announced by the US Department of Energy, and we are actually approaching the announcement approval of CD1, which is also a big step to move forward. So here in the bottom left picture shows a board view of the EIC accelerator. The future EIC will operate both polarized or unpolarized electron-proton collisions and electron nucleus collisions. So for EP collisions, the beam energy for proton beams will vary from 40 to 275 GeV, and for the electron beam, it will vary its energy from 2.5 to 18 GeV. So another big achievement will be pursued by the future EIC is the incident luminosity is vary from 10 to 33 to 10 to 34 per centimeter square per second, which is a factor of 1,000 higher than the last generation DIS collider HERA. The bunch crossing rate is about 1 to 10 nanoseconds, which is much faster compared to existing RHeC and LHeC operation. A new and unique feature will bring by the future EICs, we will operate various E collisions with the nuclear species vary A number from 2 to 208, provide different nuclear environments for the fundamental question studies. Heavy quarks play a special role in the EIC sense portfolio. According to the factorization mechanism, the mirror high-flow jet and hydrogen cross-sections, as illustrated in the bottom equations, contain information about both initial nuclear and nuclear Parton densities, especially the high-flow product can provide further constraint for large Bilkin X region. And also it contains the final state fragmentation processes. So as shown in the right plot, for example, the group fragmentation functions has different prediction from different model, and there's large uncertainties or discrepancy in the high Z region, meaning the hydrogen carry a large multi-fraction compared to the parent Parton. Meanwhile, the heavy quark nuclear transport properties are predicted to be distinctly different from light flavor quarks, will give a unique discriminant power between different models as shown in the left. So we propose to mirror the nuclear morphism factor of different flavor hydrogens as a future EIC to prove the hydrogenization in medium. So in the middle, we're showing the early projections at the event generation level for the different flavor hadrons, for example, like a black for the light flavor pions, D-meson and E-meson as function of hydrogen amount fractions using one ESA collision energy. We compare with two different model predictions, where the dashed line refer to the absorption model and the solid line refer to the Parton energy loss model. So just compare the dashed line and solid line, you can see using only light fluid measurements, it's very hard to distinguish or separate different model predictions. If you switch to the heavier products such as D-meson or B-meson, you can gain tremendous or strong discrete power to separate the different model predictions. And also the theoretical prediction indicate the high flow fragmentation modification in EA collisions doesn't equal to light flow fragmentation modification in EA collisions. How to measure heavy quarks in ESC? So actually the hadrons contain heavy quarks can be identified by detector using their unique lifetimes and masses. As shown in the right table, we just compare the mass and the average decay length or lifetime, times theta. For the D-mesons shown in the green color and B-meson shown in the magenta color, they are very different. So to measure high-flow products as ESA, the detector are required to satisfy the following requirement, meaning fine spatial resolution for display vortex reconstruction, fast time resolution to suppress backgrounds from neighboring collisions, low material budgets to maintain fine heat resolution. From the initial simulation studies for the future ESA, this is in EP collisions, we started generate D-meson and also D-meson decay daughters, the kinematic distributions. So you can see the particles produced in the asymmetric electron proton and electron nucleus as the future ESA has a higher or larger cross sections in the high surface region. Therefore, the ESA detector is required to have large granularity, especially in the forward region. To meet the high field physics environment, as I mentioned in the previous slides, a silicon vortex and tracking detector with low material budget and fine spatial resolution is needed. The concept design for a proposed forward silicon tracker detector has been carried out in Jiang simulation within the Feng framework. So the proposed forward silicon tracker detector carried by the local Nano project, ESA project, has the surface coverage from 1 to 3.5, and it consists of 3 planes of monolithic active pixel sensor, reference maps, silicon detector, and 2 more forward planes of high voltage maps, silicon technology. So the geometry has been started in different concepts. So in the left is kind of like a refer as one design is the Nano designed forward silicon tracker integrated inside a base magnet and integrated with the viral silicon tracker and the forward reach and jam tracker. Different geometry also has been explored. So in the right picture, just show you another example is we more optimize the Nano FST with a reduced auto radius to fit into the time projection chamber in the ESA detector. And you can learn more detail from this archive paper. To reconstruct hadrons, we established and developed the full analysis framework, which includes the event generation based on PCR, detect response in Jiang simulation, beam Raman, and QCD background. So based on a particular detector design, for example, shown in the bottom left, we focus on the reconstruction of the family of D-mesons, and in the right 3 panels, we show the mass spectrum for the reconstruct D+-, reconstruct D0 and its antiparticle, and also the reconstruct D sub S. So we see clear and pronounced signals and very good signal back ratios for all the reconstruct D-meson families. And the different detect geometry and the reconstruction also has been started. So based on the reconstruct the D-meson, we also reconstruct B-meson. We update the projection on the nuclear motivation factor as a function of hydrogen PD for D+- shown in red and for B+- shown in blue, according to this red equation. So this is an inclusive study, and you can see the high flow measurement as ESA really can have a good precision on the low PT environment, like from 0.5 GeV up to 7 GeV. In addition to the projection on the statistical uncertainties, we also update and evaluate the systematic uncertainty based on the different detector designs and the corresponding performance, and also the different magnetic options. Beyond the inclusive high fluor studies, we also correlate the recontract high fluor hadrons with their parent jets. So later on, I will introduce the fluor tagging jets studies. So after the correlation between the hadron with the parent jets, we update the projection on the projected nuclear motivation factor REA as a function of the hadron momentum fraction, which defined as the hadron momentum relative to the parent jet momentum. So due to this jet tagging additional jet tagging efficiency, everybody is kind of slightly blew out, but it's still kind of within a 10% for the big mass environment, and we do obtain pretty good statistical uncertainties for the charm environments. And also these observables will provide good discrete powers to separate different model predictions. So since we have good statistics in the charm reconstruction, we actually separate the kinetics of the charm products and look into the solar plate dependence. So in the left panel, we separate the D-meson reconstruct D0 D-meson kinetics in 4 different solar plate regions. So from the top left scan to the bottom right, we increase the solarity of the reconstruct D0 from -2 to 0, 0 to 1, 1 to 2, and 2 to 0.5. So you can see the signal vacuum ratio slightly increase, is due to the detector performance and also the lower cross section. And the right is the corresponding project nuclear motivation factor statistical and systematical uncertainties in the corresponding 1E ES operation for EP and the electron gold collisions. From the bottom to right, we increase the solar activity of the reconstruct D0. So even in the 4 region, we also obtain pretty good, uncertainties for the future ES equation.
You have 5 more minutes.
Sure, I think we're on time. Thank you. So recent 6 relative development also includes the next order particular QCD corrections. So there are some recent updates from the theoretical side, and you can learn more details on this paper. So then we compare our projections with the theoretical predictions based on one particular model, which is the Parton energy loss model. So here is, for example, we look into the PT-dependent REA for the reconstruct D-mesons in 3 different solar regions. So from left to right, we increase the solar region for reconstruct D-meson from backward, central, and forward. The theoretical prediction has been normalized by the inclusive hadron production. Therefore, this shaded band referred to the theoretical prediction has mitigated the initial PDF uncertainties. So it's mainly dominated by the final state hydronization processes. So we provide our projection, shown in the points on top of the theoretical predictions. So this study indicates, especially in the 4 repeated environments, the EIC high-flow products has enhanced sensitivity to the hydronization process in medium, can provide a further constraint for the theoretical prediction. So beyond the D-meson study and B-meson studies, we also extend our high-flow probe to reconstruct high-flow hadrons and high-flow jets in the simulation, including the various detector performance. So for example, in the lab, we also study the reconstruct lambda C, which can be used to study the ratio of lambda C over D to check, the fragmentation difference between the baron and meson. And also we study the flavor tech jets for the light flow jets shown in black, charm jets shown in red, and bottom jets shown in blue in EP collisions, based on indicated algorithm and using the display vortex method. We also explore new observables such as the jet structure, in a different analytical description, like the defined as jet angularity. And you can see the definition shown in this equation and learn more details from this paper. So this jet angularity is actually correlated the hadron inside jets with the parent jets, from the PT and also the eta-phi correlation with a certain A power order. So therefore, in implications, we compare the jet angularity distributions with 3 different A values from 0.5, 1 to -1, and compare the distribution with a particular A order selections, compare the distribution between light fluid jets shown in black open points and the charm jets showing the blue closed points. The bottom is showing the ratio of the normalized yield on the jet angularity between the charm jets and for the distribution of the light fluid jets. And for all 3 different selections on the A values, the jet angularity between charm jets and light fluid jets are very different. So this data is shed light into how quarks and gluons recombine into final state hadrons with different masses, and the impact by nuclear medium effect will be started in equations. Now come to my summary and outlook. So we have achieved pretty good progress and results for the EIC high-fluent jet studies with detect performance evaluated in full simulations. The new high-fluent jet program for the EIC will explore the fluid-dependent Parton engine loss in medium and the hydrogenization process in the poorly constrained kinematic region, such as the large Z hydron mounted fluxation region. We actually look forward to work with more collaborators and contribute to the EIC realization along with this forecast timeline. And just a highlight, we expect to achieve the CD1 improvement by DOE pretty sometime this summer. So that's all for all my presentation. Thank you for your attention.
Thank you very much for this great summary of heavy flavor physics at the EIC. Are there any questions? Yes, I see one raised hand. Uta.
Yeah, thank you very much. I'm not sure if I got it correctly. You mentioned a spatial resolution of 100 micrometer?
Exactly, yes.
Yeah, this is the impact parameter resolution, yeah?
Exactly. It's impact parameter, or you can define the distant or close approach. It's really measures the separation between the decay vortex and the prime vortex.
Is there any reason why it's so rather large? Because, for instance, at Atlas, with our inner B layer, we reach 5 micrometer, but typical is 10 micrometer. And even LHCb, of course, which is rather forward, has 10 micrometer. So I was a little bit puzzled about 100 micrometer.
I see. So this 100 micrometer, can you say this kind of like with one particular design with a large, stronger magnetic field? So we project the track DC2D is along the transverse plane resolution as a function of track PT. So because EIC particles really can push to the low moment region, around 1 GeV or 0.5 GeV, that's the large resolution show up. So we just gave a roughly cut, okay, better than 100 micron. But overall, if you switch, high PT tracks, for example, PT larger than 2 GeV, we can definitely achieve like a 20 or even 10 GeV. Sorry, not 20 or 10 micron, sorry, yes.
Okay, thank you. This clarifies this a bit. Thanks.
Thank you.
Okay, thanks for the question, and thank you again for the presentation. So let's go to the final presentation for the morning session, and that will be Hervé, who will talk about the deconvolution problem of deeply virtual Compton scattering.
Oh, okay, thank you very much. Can you hear me?
I can hear you well, and I see your slides, but not yet in full screen.
Oh, I saw the way. Does it work?
Yes.
Oh, okay, very good. Thank you very much. Hello, everyone. I'd like to present here the work we did with the collaborators on the deconvolution problem of deeply virtual Compton scattering. So you may find more technical elements in this preprint on archive. So with the current publication of the EIC yellow report and the Chinese proposal of the EIC and other facilities, deeply virtual Compton scattering will enter an era of more precise data and also a new kinematic range. So since it has already provided many experimental data and already fits have started to extract generalized Parton distributions from this data, I think it's important to reconsider the question of extracting in an unbiased way, so not a fit of a model, GPDs from DVCS data. Sorry. Okay. Going very briefly again on this DVCS. So this scattering of a lepton on a hadron target via a photon of large virtuality. And you have an intact proton in the finite state and a real photon. So we express generalized Parton distributions in terms of these three variables, where x is the average longitudinal momentum of the active Parton inside the target. Psi describes the transfer of longitudinal momentum, and t is the usual variable. Here you can see the diagram of systematic depiction of the process with the hard scattering part and then the soft non-perturbative part here. So exactly like in DIS, the amplitude of DVCS can be parameterized in terms of structure functions, so the Compton form factors, which write as a convolution of a coefficient function calculated in perturbative QCD, and your Parton distribution, so the GPD here, that encodes a non-perturbative structure. So I think the GPDs have been mentioned several times already this morning, so they are of great interest, for instance, for tomography program. I chose here just to illustrate another hot topic of GPD, which is extraction of gravitational form factors of the energy momentum tensor. So this is the so-called mechanical properties. You can, for instance, try to extract the distribution of pressure induced by the gluons and quarks inside the proton. Here you see a work we did, and I will refer for more detail on a presentation tomorrow by Pavel Snajda. And you see here an extraction we performed from current DVCS data in the entire world. And you see, so this is a crucial parameter for these mechanical properties, and the uncertainty is very large in our extraction, and it's compatible with 0. The reason for that is that we tried to have a non-parametric and a lesser biased approach towards the extraction of Compton form factors. Here you can see another approach with neural networks for Compton form factors. You see that this gives very large error bands. If you want to have a smaller error band, you have to rely on the models, and then you are completely dependent on your model. So what I'd like to speak a bit about is this possible for Compton for extracting generalized Parton distribution in general? So a few properties that I will use in the following. I will mainly focus on the GPD age, because its forward limit gives back the PDF, and we know that very well. And I will also use this important property due to Lorentz covariance. The Mellin moments of your GPDs are polynomials in the variable psi. So this results in, sorry, it's why doesn't it go? Oh, excuse me. Okay, I don't know if okay, good. This can be conveniently written. Okay, this condition can be conveniently satisfied with a double distribution formalism. So where your GPD writes as this integral transform of a so-called double distribution, and the D term that is precisely used in mechanical properties, many mechanical properties. So position of the problem we have here. Since Compton DVCS will give you Compton form factors, which are convolutions of GPDs, can you, from the knowledge of a convoluted GPD, extract the original GPD? So this is what we will focus on here. And in an intuitive way, you will say that the integration on X would lose information, but then you have to remember that X and Xi are related, are not free variables, are related by the polynomiality, and X and mu square are related by the evolution equations the GPDs have to obey. So the problem is a bit more tricky. The question is very old, and evolution was already proposed as early as 1999 to solve the problem, but no feasibility proof has been provided as far as I know. So what we will try to show here is that it probably will be very difficult. And to show that, we introduce a concept of shadow GPDs. So it's very simple. A shadow GPD at leading order is a GPD whose leading order CFF, so the convolution of the coefficient function times the GPDs at leading order, give exactly 0 at a given scale. And its PDF, also its forward limit, gives also exactly 0. So under evolution, it will only evolve as a subdominant evolution. So here in alpha to the power 1. And next to leading order shadow GPD is the same. Your next to leading order convolution is exactly 0. And then under evolution, it will evolve only as alpha square. And alpha square, so it's both subdominant and numerically very small. So how do we find these kind of objects? We will search for them as simple double distributions. And using a few simplifications written here, at leading order, it is very well known that the leading order CFF only probes the diagonal x equals psi plus the subtraction constant, but we will neglect the d term here. So in the end, a leading order shadow GPD has simply its diagonal, which is 0, and its PDF, which is 0. So in order to find them, we will search for them as polynomials, since polynomials can approximate almost any continuous function. And if you take a polynomial double distribution, you can compute its GPD. You will find this form here. So it's a linear transform. And then if you want to cancel the diagonal, you will find that it simply amounts to solving a linear system of n+1 equations here, where you can recast all your equations into a simple matrix. So I give the formula of the matrix here. The important point is the matrix of n+1 equations, and the number of parameters you use to parameterize your double distribution is quadratic in n, because it's a polynomial of order n in 2 variables. And we also want to cancel a forward limit. And here again, same story, n+1, n+2 here equations, and again, n square variables. So you are sure to find solutions to both these systems, and you're sure to find an infinite number of leading order shadow double distributions. Here you can find some of them. Now, that is interesting, but in order to find a more convincing argument, we decided to go at next to leading order. So it's the first time, as far as I know, that this is studied, to find GPDs, shadow GPDs, which under evolution would only evolve as alpha square. So the next to leading order CFF is composed of 2 parts. So you have a collinear part, and you can show that the collinear part can be again written as something times the leading order plus, oh, here again, same general structure, n+1 new coefficients that you can enter in a linear system. And the full one loop part can also be written in terms of the collinear part plus, again, a new system. So you can cancel your 2 systems and you will find solutions. Here I show an example of next to leading order shadow GPD. So you can see that it's exactly 0, for instance, on the diagonal, it's exactly 0 on the PDF here. Now, what is interesting is how does it behave under evolution? So I take the psi equals 0.5 line, and we perform evolution to extremely large values of mu. And here we plot how the GPD evolves with scale. And you see that overall, the GPD in some places evolves with of order. The evolution is of order 1, so it evolves in a large way. But for x equal psi, so here psi equals 0.5, you see that the GPD almost does not evolve at all. The derivative is extremely small. So here we have a GPD which is 0 at a given scale and on the diagonal, and which under evolution will keep the diagonal, which is extremely small. So it's very, very difficult to identify this object either at leading order or at next to leading order, actually, because it's designed in this way. Yeah, let me show you an example that may be more striking. So in a level arm of Q square in 1 to 100 GB square, which is typical of future collider kinematics. So the next to leading order CFF generated by the previous GPDs that I just showed you, both varies at alpha square, and it is also of order 10 to the minus 5. It's 100,000 times smaller than the GPDs that I showed. This means, in practice, here you have the very popular Gorskov-Kroll model at scale 1 GB square. You could add shadow GPDs. Like here, I added two of them, two with a very different shape. You see, you cannot make the difference between these three curves, the blue, the brown, and the orange one, using only DIS, so the PDF, or DVCS data. I mean, they're virtually indistinguishable on the entire range of 1 to 100 GeV square. So what we've shown here is an explicit demonstration of the existence of certain types of shadow GPDs, which, although they have a considerable size, they generate only a very small and subleading contribution to Compton form factors. And so they will be completely hidden in the typical statistical and systematic uncertainty of DVCS. So several other popular channels will suffer exactly the same problem because they have the same kind of convolution and the TCS leading order DVMP. Now, if you find another process, such as, for instance, next to the order DVMP with another coefficient function, you will be able to discriminate to some extent these DVCS shadow GPDs. But it is to be feared that these processes also have their own shadow GPDs. So, for instance, a process that it seems promising with respect to this is double DVCS, because it will give you an access. I mean, the dimensionality of your experimental data is such that the inversion problem is posed in a very different way. Or if you get lattice QCD with a full functional in the X space, it will bring a very different view on this problem. In order to perform an extraction of a generalized Parton distribution with a lesser systematic uncertainty, what was the point of this presentation is to advocate for multi-channel analysis, because DVCS alone, even if a larger Q-square range is, of course, very needed to increase the quality of the extraction of GPDs and, for instance, proton mechanical properties, a multi-channel analysis is probably necessary. I mean, is necessary to get rid of model dependence on this GPD's extraction. So why is it important? Because it has an impact, for instance, on hadron tomography. Since you extract data as a value of psi, which is different than 0, you will need to perform the extrapolation to 0, be sensitive to this phenomenon during this extraction. You'll be all the more sensitive to that because the GPD that is required for orbital angular momentum, for instance, has a forward limit that is far less constrained than the GPD-H. Of course, to progress also on this question, I think the more theoretical constraints could play a significant role. For instance, positivity, we know will probably bound the range of variations, at least in certain kinematic regions. And so I think an effort on a new theoretical constraint would be required for this. So thanks a lot.
Thank you very much for this detailed overview. Questions? I don't see any hands up. So you gave a very specific snapshot. Could you give maybe at the end a general update what the status of the Partons project is, particular with respect to measurements at JLab 12, Compass, but then also future measurements, maybe EIC and EMBER?
Oh, okay, so measurements of Compton form factors, you're saying. Because here the point was to anticipate, let's say, the production of Compton form factors of much better quality than those we have right now. Because so extraction of Compton form factors like world data extraction have been already performed using neural network to try to have an unbiased estimation of this. And of course, in regions of, for instance, large Q square or low Q square, I mean, as soon as you drift a bit away from the current very narrow region of experimental data, the uncertainty on your Compton form factors increases a lot. And this is the reason why in this kind of unbiased studies, you end up with, when you try to perform an extraction of any phenomenological data, you end up with this very large error bars. And so far as the approach has been to then fit with rather constrained models, and so you shift the uncertainty, you hide it actually in the systematic choice, in the systematic uncertainty of choosing a specific model. So here we were advocating that so this is so far the only extractions of GPs that have been performed, as far as I know. So choosing a specific model and then fitting the model. So I think it would be nice to have more effort on lesser parametric extraction. And I think GLab 12 will provide data which are more first more precise and also in a slightly larger Q-square range. But then the EIC range is very desirable for this kind of issues.
Okay, and we have now one more question. Uta, please.
Yeah, perhaps just from my understanding, since you mentioned that you extract H, which is of course unpolarized as far as I remember, are you also considering the DVCS cross sections as measured with Hera? Because those are of course at very high Q-squared in comparison to JLab and EIC. Are those fitted as well? Because I somehow missed somehow a description of the data sets that you are using.
Of course, so I did not intend to make a detailed presentation of this specific extraction. So yes, in this fit, as far as I remember, almost the entire data set of world DVCS data is used. So including this error data, but the error data, I've not performed myself the extraction, but as far as I remember, they are rather scarce points. So not so many points. Is it?
Yeah. This is just a cross section. Yeah.
So I don't think it provides
a few data points.
I don't think it doesn't provide. It provides a very strong constraint on the extraction actually.
Would it be, if I'm just allowed to ask, also interesting if you would have a potential in LHeC and DVCS data points even at much higher Q-squareds than Hera, so factor 15 higher?
I mean, it would be, and especially for this matter of properties, it would be extremely, if you get the theoretical mathematical limit Q-squared tends to infinity, you make the problem almost trivially invertible. So if you have a very, very large range in Q-squared, it's extremely desirable for the mathematical question of inverting these integrals. Yes.
Yeah, thank you very much. Perhaps we can follow this up. Thank you.
Okay.
So let us at this stage thank all the speakers again for making this a very interesting session. Thank you all for attending and asking really excellent questions. And that concludes the second session in future experiments and facilities of today. There is one more after lunch break. We'll start at 12:15 Eastern time. That is 6:15 Central European time. Thank you very much.